Thanks, Sarah. So, as Sarah said, this is a presentation on automatic rock physics model calibration. We're optimizing via a method that we call segmented averaging to speed things up. This is a presentation based on some work done by myself, Kushal Gohil, and my colleague SN Naini at Science Analytics a little over a year ago. And this presentation will be very similar to one that was presented at the EAGE back in October. So it's really the same project, but just the presentation's been updated a little to our template and with a couple of extra slides. So the first question I guess I should answer is, why are rock physics models useful? From the names on this call, I know that at least a few of you are very familiar with them, but for anyone that isn't, rock physics models are useful because they allow us to do log filling or log prediction. So we can fill in gaps or predict missing logs where we have them, or where we don't have them in fact. They allow us to do what-if modelling. So if we wanted to say, what does this rock look like with, 3% extra cement between the grains? What would that do to its elastic properties? They could be useful there. And they allow us to infer details about the rock structure. So if we know that, let's say we're working with a sand, and the only way that we can get a sand model to fit that we know should be applicable to this particular sand we're looking at, if the only way we can get it to fit is to add a certain amount of sand or to change the sorting to a certain degree of pore sorting, then that by inference kind of gives us information about the sand itself and allows us to then infer further things about the flow properties or its compaction behavior if we were to change the pressure that might not be immediately obvious from the log results that we measure in the well, but because the rock physics models use a mathematical model of the physical arrangement of a rock, by inferring these things we know that they're likely to be the case in the rock. So that's why they're useful. Why do we want to automate the fitting of these? Well, firstly, it's going to be faster than an expert doing it by eye or by hand. Secondly, expert knowledge is not needed, so we can democratize access to rock physics models. We can make them a more generalist tool by taking out the need for expert knowledge to fit these. Obviously there will still be plenty of work for experts to do, but just the fitting process and the basic use of these will not be something that they need to be doing. And finally, a more complete consideration for data set. So as you'll see in the following slides, when we fit a rock physics model, usually in the manual process, we isolate just a small subset of the data and fit to that because of the limits of humans interpreting data. However, when we use a computer to do this, we can consider the whole set of data and fit in a slightly different way, but one that considers everything in the data set and is less biased by interpretive considerations. So, the first question I think probably a lot of you are going to be asking now is, why don't we just use machine learning models? Science Analytics is known for its machine learning technology. We've been around for a while and constantly been saying, hey, machine learning models are great for filling in logs, and they are great for filling in logs. We can do a really good job of filling gaps in logs, or even predicting logs where they're missing, should we have a large enough data set to build a model from, using machine learning. And there's a whole range of different models that we can use for that. There's random forests, XGBoost, various different types of neural network, and things like support vector machines as well. There's loads of different models, and they get really good results if you pick the right one and you've got some decent training data to go on. The models can also be trained on a local or regional basis so that they reflect local trends in your data. So they're not constrained to kind of just the mathematics that are originally programmed with. They can actually be tailored to your local area, take account of local trends, local changes, even local variations, so you can put in the well's position as a variable and have the properties that you're predicting vary from one side of the field to another. So they're really flexible in that sense. And also the models can take advantage of input data that rock physics models don't take advantage of. So there's very few rock physics models out there that would see any use in a resistivity log. Most of them want porosity and V-shale and that kind of thing, but they don't tend to want resistivity or other logs like that, maybe SP. But rock physics models will take any log that you give them, and if they're useful to the prediction, it will use them. So, machine learning models will take any log that you give them, and if they're useful, use them in the prediction. So rock physics models can take a much larger amount of input data, factor that all into the calculation, and hopefully could come up with a better constrained and more detailed prediction as a result. So these are all great things about rock physics models. Sorry, about machine learning models. They shouldn't both contain the word model. That's what's getting me confused. But these are good things about machine learning models. The two things that they don't really do so well at is, first of all, machine learning models can only predict geology that they've seen. By seen, I mean data that's present in the input label set that it's training on. And then machine learning models are not constrained by physics in most cases. And these two limitations mean that if you wanted to model something that you know should be there, logically and geologically, but you don't have a sample of, it makes it very difficult for the machine learning model to predict what you would see there. And equally, the machine learning models, unless they are constrained by physics, which is something that people are working on, but for the most part, the standard models are not constrained by physics, which means that they can predict things that can't physically happen. So you then have to go and check your VPVS ratio, your Poisson's ratio, other behaviours to ensure that what they've predicted is reasonable. This first point here, or I guess it's the fourth point on the side, but the first kind of downside of machine learning models, you can imagine if you had all your wells drilled in the field, but you knew that elsewhere in the field you were expecting some more highly cemented behaviour, and you wanted to know what that would look like, there'd be no reason that you would have drilled a well deliberately through a highly cemented sand. But if you wanted to know what that looked like, a rock physics model could be a really good way of modelling that and getting some elastic responses to see what that behaviour would look like if you were to drill a well through it with a fair degree of accuracy. So to show you the method in practice, the method of auto-fitting a model, we're going to use an example model as some example data. But I should highlight that the model that the method we're going to discuss for fitting is generally applicable to all kinds of rock physics models. So we're going to be using the constant cement, but we've also tested this with the friable sand, the contact cement, the Zupane, and the Avseth kites model as well. So it works generally across all these models. We just chose constant cement because it has a fair degree of complexity, so it's a good proof of concept. Also, in all the future slides here, we'll only be looking at the sand in our example data set, so the orange points shown in this plot. This plot shows the entire data set, so it's the sand and the other materials, where the other materials are, for the most part, shales. But in all the future plots, it will just be the points shown in orange here that are used. The grey points will simply not be shown. But the points shown in orange here will be coloured different colours depending on what we're trying to show. So they might be coloured to show a degree of V-shale or V-sand. They might be coloured black if we try to contrast them with something else, but it will only be these orange sand points shown from here on in. So the first example of that, we see an example of how we conventionally fit a rock physics model. So typically what we do is we identify the highest quality sands, so what we call the clean sands. In this case we've gone for above 90% V-sand. And we then display our rock physics model as a line. So the sand points are substituted to the brine case, or sometimes people do this in the dry case instead. But either in the dry or brine case, you have your substituted sands, which are clean, and then you have a line that represents your rock physics model for the clean sand and either dry or brine saturated case, depending on what you substituted your data to. You then adjust the fitting parameters. So there's a number of different inputs to most of these rock physics models. So things like the coordination number, the degree of segmentation, the shear reduction. There's all of these different values that can be changed to adjust the position of this line. And you adjust them until your line appears to be a good fit to the clean sand behavior in your plot. And this requires interpretive skill, time, experience and knowledge if you're going to do it well and come up with models that are a good predictor of your rock's behavior. Putting that process into a flowchart, for reasons that will become clear on the next slide, your inputs are a porosity range, so in this case 0 to 35% porosity, mineral volume fractions as well, and mineral properties. The volume fractions and properties go into a mixing model. So as we said, this data cloud here is between 90 and 100% sand for the orange points. So we'll probably put in 95% sand, 5% shale into our mixing model. That gives us mixed mineral properties, which we then put into the constant cement rock physics model. That then gives us a dry bulk modulus and dry shear modulus for a rock made up of grains that are 95% sand, 5% shale. And then we do a Gassman fluid addition to add the brine properties in, assuming that we're fitting in the brine case, not the dry case. That gives us brine case bulk modulus and shear modulus, which we can then plot in here as a line and adjust these green parameters so that they fit the line to the cloud of data. So this is the standard way of fitting a rock physics model, that you adjust these parameters until you get a visual fit here. So how can we get a machine to do this? We add a couple of extra steps. So we add a calculate misfit and a cost value at the end here, and we'll come on to what the cost value is in a second. We also make a couple of changes to how we're doing this. Instead of calculating a line, we calculate a cloud of points. So we calculate the rock physics model prediction for every point in this cloud. That means we take in the porosity log rather than the porosity range. So we take in the actual log values of porosity at every point through here, not just the range of 0 to 35%. We also take in the mineral volume logs, so the V shale, the V sand, rather than an average V shale across the whole data set, or across the area of interest, as we said before when we were fitting in the example case. It was 95% shale. Now we're actually going to use the whole V shale log. We then put those into a mixing model to give us inputs to the rock physics model, which then makes dry bulk modulus and shear modulus logs. We then put in mixed fluid property logs, so we actually use the saturation logs and the fluid properties to calculate the fluid properties to add into each sample by gas and fluid addition, which then gives us in situ bulk modulus and shear modulus as logs, which we can then display here as a cloud of points. What we can then do is on a point-to-point basis calculate the difference between the original point and the model point, and add those all up in a way that I'll show you in a second to give us a cost value. And then we simply want to minimize this cost value because we want to minimize the misfit, so we do an iterative optimization, changing these green parameters to minimize this cost value. If you're wondering what the cost value is, we measure the distance between each measured point and its corresponding model point, and take the square of that difference and add them all up across the data set for both bulk modulus and shear modulus, and that sum of squared errors gives us our cost value, and that's what we're trying to minimize. So the benefits of this approach. Well, first of all, we calibrate our rock physics models to the in situ case, not the dry or the brine case. And according to Draga, in his paper in 2018, that is less likely to lead to errors because rock physics model outputs are likely to conform to the Gassman assumptions, whereas the values in measured logs often are in breach of Gassman's assumptions. And where they're in breach, the substitution result you get can be wildly off. So it can be really skewed. So that gives you a larger error value. So effectively, if you look at the little boxes below, what we're doing is we're going from the RPM in the dry case, substituting through to the RPM for the in situ fluids, and then we just compare that to the log for the in situ fluids. What's typically done when you're doing calibration by eye is you do the rock physics model to the brine case, and you also substitute the in situ logs to the brine case. So you do two substitutions instead of one, and compare them both in the brine case domain, for want of a better term. And the problem really is here in this log to brine case substitution. If you have rocks that don't quite satisfy the Gassman assumptions, then this substitution can give you strange results. Obviously, that's mostly taken care of in the traditional approach by only using very clean sands, which means that you satisfy the Gassman assumptions for most of the points, but that does limit you to very clean sands. Whereas here, as we see in the second point, we are calibrating to all the points of the matching mythology, not just the cleanest points. So you remember I said that all of these points were sands, and then we had selected for the manual calibration just this very clean sand end to this cloud of data points. Whereas the machine learning, or well, not machine learning, but the automatic calibration is actually using the entire data set and trying to model a fit to the entire data set. So that's the difference between fitting to just this orange subcloud or using the red modeling option to fit to everything. And you can see that we get a more complete consideration of the data set using the red. And you can probably debate whether this is an appropriate thing to do or not. So one argument is that the rock physics models are designed for sands. Mathematically, they're constructed for sands, and so you can say that's where we should fit them on the purest, cleanest sand possible, because they're designed to model sand behavior. But the other argument is that we're going to want to use this rock physics model to model everything that we're calling a sand. So everything that's labeled as a sand in our mythology log, we want to use the machine learning, we want to use the rock physics model to predict a gap in, potentially, or to predict a change to, if we were looking at maybe changing cementation levels. So what we want is to fit that rock physics model across the whole of that range of data so that we know it's a good fit, not just for clean sands, but also for dirtier sands. And finally, calibration could take into account compaction trends. So we could use depth trends in here. And also, with some sensible guidelines or restrictions, we don't need expert knowledge to make use of these RPMs. So because we're taking care of the fitting part of this, we really just need some guidance for the user in terms of which model to pick. So we need to know, okay, area by area, what's the more appropriate sand model or the more appropriate carbonate model? And then perhaps just the user just needs to tell us, okay, I'm looking for something to model my sands, to model my carbonates. Perhaps we can have a bit of information there to say, okay, this one's particularly suited where you've got cementation, this one's particularly suited where you've got particular types of carbonate porosity. But overall, we can take out quite a lot of the need for expert knowledge, and then we can basically give this option to any user, and they can use the auto fitting to get a good match between their data and the model results. So the one disadvantage of this, before I move to the next slide, is that originally when coded, this process was quite slow. If you use a global optimizer to do this, even if you use one of the quicker standard global optimizers, it does take a while. I think in our initial test, this was taking 5 to 6 minutes to run on this data set, and that's really too long for a user to wait. So we came up with an acceleration strategy that seems to work quite well. We call this a two-stage acceleration by something we call segmented averaging. And the idea here is that in the first stage, you simplify the data set to a small number of segmented average points. So we take a couple of averages across the data set. In our case, we actually use 40, and that seems to work well. And then we use a global optimizer to find the best parameter values to fit the model to the real data, well, to the average data set. Global optimizers tend to be slow, but because we're simplifying the data set from thousands of points down to 40 points, we have a much smaller data set, so the optimizer can run much faster. So this is stage one: simplify the data set and use a global optimizer to find what turns out to be a rough best fit. So it gets you almost to the best fit, but not quite. And then in stage two, we take the outputs from stage one, which are our rough best fit location for the model, and we use a full data set. So we use all the thousands of points that we originally had, but we use a local optimizer. And local optimizers tend to be faster than global optimizers. We use that on the full data set. So we do the last little bit of optimization using a local optimizer, and that gets us to the true best fit location without it taking so long. So by using this two-stage approach, we got our fitting time down from about 5 or 6 minutes to 30 or 40 seconds. And some of this can be pre-computed, so in practice we could probably have this run even faster. So a little bit about segmented averaging and the approach we're using. What we have in this example here is the original data shown with the color that indicates the V sand. So the orange being the cleanest sand and the kind of the grayish orange being a dirtier sand. And then we have a poorly fitting model, and I've deliberately chosen to make about as poorly a fitting a model as I could here as an example. We can see that they're poorly fitting by comparing one cloud to the other. What we could also do is we could take an average of each cloud. So you can see if I took an average of the well data, it would sit where this green point is. And if I took an average of this model, it would sit where this pink point is. And by comparing the two models, or the two averages, I can say, well, if the average is bigger, or if the difference between the averages is bigger, I've got a more poorly fitting model. And you can imagine if this red cloud of points was to become a closer match to the orange and grey cloud of points, this average would also shift upwards and become a closer match to the green average. So we can see that comparing averages could be a way to approximate model misfits. However, there's one problem with this, which you can see here. If we were to simply lift the low porosity end of the model and keep the high porosity end down here, so this red cloud of points, if we basically to tilt it more steeply, we would get this pink point to move upwards without really increasing the quality of the match at all. Using a single average is not so good. So what we actually do is we use multiple averages, as you can see in this second point here. So we look at the green and the pink points here. By using multiple averages, we get to account for that gradient across the model to work out, okay, how good is the fit. And we're still simplifying in this example down to 4 points. In the actual code, we use 40 points over a 40% porosity range. The other thing that we're doing here is that we actually take this, instead of making all the data and then averaging within each band or within each segment, as we've shown here, what we do is we take the average porosity point, the average V shale point, the average saturation values, the average mineral properties, and the average fluid properties, and we actually take those averages and put those into the rock physics modelling process to get out a rock physics modelled average point. So instead of working with the whole data set and then averaging to one point, we average to one point, then rock physics model to get the equivalent point in the rock physics model. So we reduce the amount of work the rock physics model has to do by reducing the number of points. So in this example here, it would be the rock physics model has to compute on 4 points. In reality, we do that on 40, as I said. The one obvious problem here that you're probably thinking of is that rock physics models are not linear. So the average of the model does not equal the model of the average. And that is true. However, when you segment this down into 1% porosity bands, the rock physics model becomes close enough to linear that we can say that it's a fair approximation to use the averages. So it's not exact, but it does well enough that it gets us to fit. So you can see here in this second cross plot that if I was to now improve the quality of my red model, all of these pink circles would move up to match the green circles, improving the match between each of them. So the distance between each pair of green circles and red circles would be an effective indicator of model fit. And if I was to just lift this model, or perhaps change the angle of this model, it might improve on some of these, but it would get worse on others. And so that would no longer be a way to trick this method, because we're using multiple different average points in different segments. When we actually do this, we obviously explore the parameters. So we use this as the misfit calculation, and we explore mixing weights in a sensible range, critical porosities in a sensible range, and so on. And when we do that exploration and try to minimize the misfit, this is an actual example of what we get. So this is an example from the code itself. So this is showing us the data average, the true data average in red, and then the true data average in green, and the model average in red for each of these segments, run over 4 segments of this data set. And you can see that they're now a very close match. So we've managed to find some properties, so some mixing weights, critical porosities, coordination numbers, and so on, that produce a close match between these average points and a model from these average points. So that allows us to get a close match, and we take the property values, so the mixing weight, critical porosity, coordination number, and so on, that gave us that good match, and we use them in stage 2. Stage 2, to remind you, is a local optimization using this full data set. So we take all of these data points in stage 2, and we start off with the model that was the best fit in stage 1, and we then use a local optimizer to just fine-tune those fitting parameters until we get to the best parameter values possible. And this is the result of doing that. You can see the two-stage model in red, the original well data in black in the background here, and we actually have the 40-point averaging from the original well data in blue, and then the green data is the rock physics model 40-point averaging fit. So you can see again that the segmented averages gave a fairly good fit, and then we've iterated to fit the whole cloud to the original data as far as possible. And this is done, as we indicated earlier, in both the bulk modulus and the shear modulus domain. So you see the fit is also fairly good in the shear modulus domain. And that's true for the previous stage as well. We fit in both bulk and shear modulus together. To give you an example of how this kind of sits in parameter spaces here, we've got some parameter space maps. So this shows us for each pair of fit parameters, so coordination number, critical porosity, Hashard-Strickman weight, shear reduction, and cement fraction, where our various points are. We've blown up one of them here so we can see it in more detail. The pink cross is our global optimized final point based on a set of segmented averages. So when we average the data and then try and find the global minimum, this is where the first stage puts us. So it says this is the global minimum based on those 40 averages. If we then put this in as our start point, and in stage 2 we take the whole data set, not the averages, and we say, okay, here's your starting point, here's the full data set, try and find the true optimum fit. That gets us to this red plus point here. So this red plus represents the true best fit location. And you can see basically the stage 1 takes this entire parameter space and gets us to this pink point. And then stage 2 takes us from the pink point to the red point. And we tried this with a number of different rock physics models, and this always seems to be something that works. The parameter space is smooth enough that we're able to use that local optimizer to find the true global minimum, as long as we've got a good starting point. And the segmented averages with a global best fit always seem to be a good enough approximation to get us a suitable starting point for stage 2. And you can see that there's various different shapes here in different spaces of where your best fit is and where there's kind of a bullseye. Some of them genuinely do look like bullseyes, like you see here in this one. Others kind of have this boomerang shape where there's kind of a band of possible best fit values. So for instance, it's like there's a trade-off here between cement fraction and shear reduction. Hopefully this explains kind of what the method is doing in more of a kind of a traditional way. So conclusions. We've demonstrated that we can auto-fit rock physics models to well data, and that with some guidance, this can be done by people without expert knowledge. The iterative auto-fitting process that we've developed fits to a more complete set of the well data. We don't just fit to the clean sands, we fit to the whole set of sands. And if you were doing this on carbonates, you'd fit to the whole set of carbonates, or shales on all the shales. Using this two-step global then local fitting process speeds up the auto-fitting over just one of the standard methods of global auto-fitting. And this two-stage process should scale well with increasing data volumes. So this is important as we go from doing this on 1 well to doing this on 70 wells or something. The first stage of this process always simplifies any data set down to around 40 points. So 1% porosity bands. So it simplifies everything down to one point per porosity band. And those points, in terms of using them in software, can be computed before the user even clicks go on the auto-fitting process. As soon as you know what your input data set is, so in terms of your VPVS density and your lithology log and your saturation logs, you can pretty much go ahead and start computing those averages. So you can compute the average VP, the average VS, the average porosity, the average density over that 40% porosity range before the user even clicks the button to go and do the auto-fitting. Second stage does require more time to compute the more data you have, but that shouldn't scale too poorly either. Further work, so things that we're going to do with this in the near future. First of all, commercial implementation in EarthNet. Right now this isn't available for users of EarthNet to apply. We do have the ability to use it internally, so if we wanted to use this on projects we can, but for external use it's not yet available, but it will be soon. For constant cement as a special case, it was recommended at the end of the EAGE version of this presentation, Parav Seth suggested that we fit in the K divided by mu domain instead, because that eliminates the slip factor from the equations. It cancels it out in the calculation. And so if we fit in K over mu, instead of doing a 2-domain 5-dimensional fit, we end up doing a 1-domain 4-dimensional fit, Then afterwards, we have to do a two-domain, one-dimensional fit to fit the slip factor. But doing those two fits sequentially is going to be computationally simpler and less time-consuming than doing the two-domain, five-dimensional fit altogether. So that should speed things up. We're also going to explore the use of ML-type optimizers in the global, instead of the global and local optimizers used here. So the ones we use here work fairly well, and they're just taken from the scikit, no, they're taken from the SciPy library. But we're going to have a look at some of the optimizers used in the machine learning methods. So things like the gradient descent method and things like that that are used in things like XGBoost, and see if those can be applied to perhaps give a faster result. We don't know if they will or not, but it's an option. And then exploration of the impact of misfit of RPMs on the logs and synthetics that are subsequently generated. So you may notice in those previous parameter space maps that we showed, there's quite large bullseyes around the best fit on each of those parameters. So if we were to misfit by 5 or 10%, would that make a massive difference? How much would be an acceptable level of misfit to still get a relatively good prediction? And might that be something we could exploit to accelerate this process faster by allowing a small degree of misfit that we know is going to be insignificant on the logs and synthetics that we generate afterwards? Finally, references to the papers that informed the work that we did here, and contact details for myself and Science Analytics more generally.